For millennia, the mysterious travelers of the solar system, comets, were thought of as omens of things to come, usually bad. Ancient texts and illustrations mark the passing of these lights with tails streaking across the night sky. They are often linked to tales and legends even of religious significance. In more enlightened times, comets were passed off as elegant balls of primordial ice and early planetary debris, heated by the sun to form their cometary tails. Like the transient asteroids dislodged from the distant belt of asteroids between the orbits of Mars and Jupiter, comets were difficult to study and little understood. When the connection was made between mass planetary extinctions of life on Earth and the strike by an asteroid, serious thought was given to these rocks in space.
There's still a lot of controversy. We as scientists, we've often had, quite a hard time coming to the notion that, rocks the size of a mountain might fall out of the sky and do life, some serious harm. Then 20 years ago, things started to change when we started to find some evidence for the death of the dinosaurs being caused by an impact. And since then, it's been suggested, a number of the other big changes that have happened to the history of life may have been caused by impact. So it's become a topic of intense study. And the arguments are still there as to whether an impact can cause a mass extinction on Earth, can affect the course of life. But it's much more widely accepted that we can't study the Earth in isolation anymore. We have to look at its place in the wider cosmos and the rest of the solar system.
To study these objects from afar with telescopes has been daunting. There was only one answer: to send unmanned probes out to get a close-up look at these comets and even take samples. Asteroids could be radar mapped and, if one dared, even landed on. Scientists and engineers around the world rolled up their sleeves and began planning some bold missions. The first attempt to fly by a comet occurred in 1985. The International Cometary Explorer, or ICE, passed the comet Giacobini-Zinner. The following year, it passed through the tail of Halley's Comet in March. In fact, 1986 was a busy year for scientists. The year Halley's Comet was on a return trip close to Earth, an opportunity not to be missed. Several probes from several nations were launched or tasked after their primary missions to intercept Halley. The Soviet Vega 1, its primary mission to visit Venus, passed within 8,889 kilometers of the comet 6th March 1986 and took 500 pictures of the nucleus. Passing through the gas cloud surrounding the coma, the probe did not suffer any system failures. The probes studied the many parameters of the comet, including density, shape, and composition. Sakigake, codenamed MST-5, was Japan's first deep space probe, and the first long-distance probe launch by a nation other than the US or Russia. It was part test vehicle for the future Suisei probe to be sent aloft some months later. Suisei was identical to Sakigake in construction, but included imaging hardware in its instrument package, including a UV imager. Launched August 18, 1985, it began imaging Halley by November. Its closest approach was 151,000 kilometers. It suffered only 2 dust particle impacts. ESA's successful Giotto was launched 2nd July 1985. This was the European Space Agency's first deep space probe. Once Halley had passed and returned to the edge of the solar system, the public and scientific excitement died down. Then, in 1994, something unexpected happened that brought attention to the issue of comets hitting planets. A little-known small comet, Shoemaker-Levy 9, was on a collision course with the planet Jupiter. All eyes and telescopes were turned to witness this event. Due to the gravitational forces of the mightiest planet in our solar system, the comet was torn into 21 pieces, and like machine gun tracer bullets, the string of cometary debris smashed into the Jovian giant with unprecedented explosive energy. Between the 16th and the 22nd of July 1994, at 60 kilometers per second, the pieces of comet struck the planet.
If you look at all the solid bodies in the solar system, you will see that they're covered in craters, and that does demonstrate that back at least billions of years ago, there must have been a period of time when the sun and planets were forming, when these collisions were really very common.
The Jupiter-bound probe Galileo was en route at the time and had the closest cameras and sensor equipment. Unfortunately, the comet fragment struck the planet on the far side, blocking the event. However, the effects on the clouds of Jupiter were clear, and infrared sensors picked up the residue energy signatures. It is speculated that each fragment would have left a crater the size of Earth.
There are still very much debates about exactly, when the impact rates were at their highest, exactly which bodies have been most affected. Also, there's a kind of discussion which almost takes on a philosophical role as well about whether or not those impacts helped or hindered life. I mean, clearly, if we're on Earth today and we had an impact of a giant asteroid, it would be very bad news. But equally, in the past, it may well be that objects like comets, which are largely made of a lot of water ice, collided with the Earth and may well have been responsible for filling the oceans of the Earth and actually helping life to begin.
The Jupiter-bound spacecraft Galileo that witnessed the Shoemaker-Levy collision was also the first probe to encounter an asteroid close up. Launched from the Space Shuttle in 1989, its primary mission was to reach Jupiter, orbit, and launch a probe into the Jovian atmosphere. En route, the opportunity arose for a closer look at the mysterious asteroid belt. It managed to pass close to two asteroids, 951 Gaspra in 1991 and in 1993, 243 Ida. Gaspra, an S-type asteroid, journeys around the innermost section of the asteroid belt. Ida, with an average diameter of 12 kilometers, was discovered to have a satellite of its own. Both these main belt asteroids orbit the Sun every 4.84 years. Ida tumbled at a stately speed of 1 revolution every 4.63 hours. Eros is an asteroid that passes close to Earth on its eternal orbit of the Sun. NASA launched the Near-Earth Asteroid Rendezvous probe 17th February 1996. Dubbed Shoemaker after the scientist Eugene Shoemaker, its objective was to intercept and study 433 Eros. Scientists wanted to know exactly how big, how dense, and what the composition of the asteroid was. Even the magnetic field was studied. The probe itself housed an X-ray gamma-ray spectrometer, infrared imaging spectrometer, a magnetometer, laser rangefinder, and multispectral camera. The package weighed 56 kilograms and was powered by solar panels. En route to 433 Eros, NEAR was in a hibernating state, but was powered up as it neared another asteroid, the 61-kilometer diameter wide 253 Mathilde, in June 1997. The probe passed within 1,200 kilometers of the small asteroid, returning imaging and other instrument data. On 3rd July, it made an engine burn, altering its trajectory, and the probe swung by Eros in January 1998, passing within 540 kilometers of the rock. The first attempt to orbit the asteroid failed due to a software failure, but a second flyby and maneuver in January 1999 set NEAR on an orbit intercept. Eros was encountered 14th February 2000. The S-type asteroid measured 13 by 13 by 33 kilometers. NEAR made several orbital changes while studying the asteroid, bringing the probe to within 35 kilometers. In January 2001, the probe made several closer orbits down to just 2 to 3 kilometers. On February 12th, the probe slowed its descent and touched down on the surface of the asteroid, the first to do so. To the surprise of the scientists, the probe survived the landing, and it continued to operate its sensors, in particular its gamma-ray spectrometer, which operated very well at such close range.
From our landing area in Utah.
NASA sent a probe to fly by Comet Wild 2 to collect samples of its cometary tail and return them to Earth. February 7, 1999, the probe Stardust was launched on a round-trip mission of 5 billion kilometers. January 15, 2006, and the probe ejected its sample return capsule that landed in an Air Force training facility in Utah, USA. The mission was so successful that another is planned to intercept Comet Tempel 1. The Japanese Space Agency launched a sophisticated probe dubbed Hayabusa. Its mission? To return a sample of asteroid material to Earth. It was the first probe specifically designed to touch down on an asteroid and then lift off with core samples, returning them to Earth for analysis. Launched 9th May 2003, the 2-year, 4-month journey took the probe to its target, a near-Earth asteroid called 25143 Itokawa, a small rock with a diameter of 540 meters and length 270 meters. The Hayabusa spacecraft rendezvoused with the asteroid and studied its shape, spin, composition and color, as well as its density and topography. In November 2005, it attempted to touch down and take samples, but failed to do so. However, scientists believed that sufficient dust particles were collected. The probe was sealed and sent on its way back to Earth. It is expected to arrive mid-2010. The two largest known asteroids in the main belt are Vesta and Ceres. NASA launched Dawn, a robotic probe, to investigate these two giants September 27, 2007. It aims to reach Vesta between 2011 and 2012. Dawn will become the first probe to orbit one object, then, under power, move off and orbit another planetary object. All previous multi-target probes have been flyby missions. The next stage of investigating the origins of comets was launched aboard a Delta II rocket on January 12, 2005. Previous missions had been flybys of comets. This one, dubbed Deep Impact, was to hit the surface of the comet with a probe and study the interior debris ejected from the collision. The impact probe consisted of a copper core of 370 kilograms, plus targeting sensors and a camera. The flyby section is 3.2 by 2.3 by 1.7 meters and housed two main cameras, one high and one medium resolution, plus infrared spectrometer and other scientific packages. The target was 9P, Tempel, 174 days travel time. The probe reached its vicinity at 103,000 kilometers per hour after traveling 429 million kilometers. The impactor separated and maneuvered itself into the path of the comet. 24 hours later, at a speed of 37,000 kilometers per hour, the probe hit the comet with the equivalent energy of 4.7 tons of TNT.
subsequent impact with the nucleus. Now, 2 hours out, the impactor basically starts its own navigation and control, performs 3 trajectory maneuvers, and then impacts the comet, creating the crater.
Scientists believed it was sufficient energy to dig a crater 100 meters wide and eject sufficient debris to analyze the composition of the comet's interior. Telescopes and sensors from several ground and space-based observatories witnessed the event, including ESA's Rosetta probe, which was passing by at 80 million kilometers. It utilized its ALICE scientific package to analyze the dust cloud from the impact with its ultraviolet sensors.
The next video shows the impactor going in and shows the view from the flyby. There's the impact, and there we have gone by. And it's all over. We get one chance, lasting 800 seconds, to take all of the key data from impact until we've flown past. And the challenge of getting all this to happen autonomously has been the really big effort that's gone on over the last couple of years.
They'll be doing that.
After the success with their first probe, Giotto, ESA set about a grander project. Rosetta would rendezvous with the comet 67P Churyumov-Gerasimenko. Once in position, Rosetta will study the comet's nucleus and its surrounding environment for 2 years. It will also deploy a probe to soft land on the comet's surface, one of the most challenging tasks ever attempted in space. Once the probe has landed, Rosetta will continue to follow the comet as it approaches our Sun. The second and successful launch occurred March 2, 2004, aboard another Ariane 5 rocket from Europe's spaceport in Kourou, French Guiana, the rendezvous now scheduled for 2014. The journey to Rosetta's final destination involves several complex flybys of other planets. It will swing by Earth a year after launch, then Mars 2 years later, followed by another Earth flyby, and in September 2008, it passed by the asteroid Steins. The flyby opportunity of an asteroid could not be missed, and considerable effort was put into getting as close to the asteroid as possible without endangering the primary mission. 2009, another swing by Earth, and then Rosetta encounters Lutetia, another asteroid, the following year. Then in 2014, the comet rendezvous will occur. The probe itself is in 2 sections. The main spacecraft is 2.8 by 2.1 by 2 meters, with 2 14-meter solar panels and 1,670 kilograms of maneuvering propellant. It houses 11 scientific instruments, all designed to face the comet in the primary phase. It will then rotate to release the 100-kilo landing probe dubbed Philae, which will carry 11 science experiments.
And comets are the most pristine materials there are available in the solar system.
Planned lander operations are scheduled for 10th November 2014. Rosetta will be a mere 1 to 2 kilometers from the comet's surface. As the lander touches down on the comet's surface, it will fire 2 harpoons into the surface to anchor the probe in the low gravity. Self-adjusting landing gear will keep it upright on any terrain, and then the landing feet will each drill into the surface, permanently fixing the probe on the surface.
There basically is no gravity with a cometary body this size, so technically you probably don't land on it, you have to dock with it. And to save yourself bouncing off, I mean, what happens with the lander is that it fires some harpoons out from the bottom of its feet when it actually lands there and anchors itself down. It has to do that. Yeah, the technological challenges about designing something that could land on something as hard as concrete or as soft as marshmallow are enormous, but, you know, we like difficult.
The lander will focus on the study of the composition and structure of the comet's nucleus material, including microscopic studies of individual grains. The end of the mission is scheduled for December 2015. There are many thousands, if not millions, of various sized rocks that make up the asteroid belt. Asteroids are continuously orbiting outside this ring in various orbits as well. These are called near-Earth objects. A team of scientists are constantly on the watch for these objects, cataloging and tracking them to determine if any could be a threat to the Earth.
2029, an asteroid called Apophis is only going to miss us by about 20,000 miles. That sounds like a lot, but it's only about 3 times the diameter of the Earth. It's going to pass much closer than the Moon, and in fact, it's going to pass closer to the Earth than the geosynchronous communication satellites above the Earth.
In the cosmic scale of things, that is uncomfortably close indeed. If sometime in the future an Earth-impacting asteroid is detected, it would be highly feasible to deflect the object from its course with accurately delivered nuclear explosives.
It is conceivable and that a spacecraft could be sent up with some sort of explosive on board or some sort of other means to deflect the object from hitting the Earth, to change its orbit very slightly.
If achieved, such an event would mark an evolutionary step for mankind and the planet Earth, which has suffered at least 3 major extinction events, most likely due to asteroid impact. By stopping another such event, man will have forever altered his and the planet's cosmic destiny.